Okay. Thanks for coming back for part two. I was going to go through the example of generating prime numbers in a fairly brute force sort of way using a list comprehension, but the example doesn't bring anything new. So I'll make a small video if you want to see how to do prime numbers in a fairly stupid but simple way using list comprehensions. So we'll push that aside for now. You've seen what you need to know really for now about list comprehensions. What I want to talk about now is something a bit new, and that's data types. So we've seen lots of types: int, integer, bool, functions, lists of all those different kinds of things. But when you want to model a particular problem domain, it's very useful to be able to define your own data types. And we're going to use the running example of data types to represent one of these things, a hand of playing cards. So we call this a hand. And the components of a hand are cards. And each card has basically two bits of information. I'm not going to worry about the picture. The two logical bits of information are which suit it is, one of these four: spades, hearts, diamonds, and clubs. And what rank the card is. That's numbers from 2 up to 10, then jack, queen, king, and ace. Okay? So that's just a recap of the English terminology for the things you know very well, I'm sure. Okay? So if we're going to write programs that manipulate cards, we could find a way of representing all of that stuff using numbers. But that brings us a lot further from the problem domain. We have this kind of layer of coding that we need to do. For example, we could define that, okay, spades is number 1, and clubs is number 2, and so on. And then so that we could have numbers to represent these, and we could have numbers for all of the cards 2 up to 14 or whatever it is. And then we would write programs, we're playing around with all these numbers, and we have to kind of remember, does that number mean the rank or the suit? Things get kind of messy. And in a lot of low-level programming languages, that's kind of what you have to do. Haskell is one of many higher-level programming languages that allow you to define your own structures and your own types of things. So that's what we're going to do today. So let me start with an example of a data type definition for something that is already defined in Haskell and plays a very special role in Haskell. But imagine it wasn't there. If we didn't have the truth values, bool, this is what the definition would look like. It would be a declaration of a new data type, and this would be the name of the type. Right? So bool is the name of the type. And then we have a list of the values of that type, where each element in the list is separated by the vertical bar. So this vertical bar here, we saw that just now in list comprehensions. Here, it has nothing to do with list comprehensions. It's just a separator. We're separating the cases of the possible values of the things of this new type bool. But that example already exists. So let's start with an example from, excuse me, start with an example from the hand of cards. And we'll start with the suit of a hand of cards. And there were one of 4 values. So we list the values: hearts, diamonds, diamonds. That's a Skånska version of diamonds. Clubs and spades. So there's an example. Simple enough. This is called an enumeration type. So this is the simplest kind of new data type declaration. This is the name of the type, and these are a list of the values where each value is separated by one of these vertical bars. So that's called an enumeration. Enumeration means to list things in order. So if I if I load this, hopefully it will actually load, yes. So if I ask what's the type of clubs, it tells me that clubs is a suit. So there you go, I've invented my, if I ask what's the type of true, it tells me it's a bool. That was already predefined. I defined a new kind of value and a type that they live in. So this is the type and this is the value. All right, I think we've got that. So when we type values, then they get typed back at us. And if we type things which are more complicated than values, they are reduced until they become a value and typed back at us. So if I have true and false, then it reduces this down to a value and prints out the value. So if I type clubs here, what do we expect to see? Well, let's have a look. We get an error. That was strange. Well, it's not strange once you understand how the little interpreter down here works. What it does is takes things, expressions, checks whether they make sense, and then reduce them down to a value, and then print the value on the screen. Okay? So if, for example, I have 1 plus 2, it reduces that down to 3 and prints the value of 3 on the screen. But the operation of converting a value into something you can see on the screen is actually a hidden function. If you want to be able to print out the value of something, you need to turn it into a string. So what is happening behind the scenes is that there is a little function called show. And the show function is the function who's responsible for printing out values. And behind the scenes, that's what's being used down here. So if I give you an example of show, if I show the value 0.000001, you can see that it actually does some work. It's actually converting the value into some kind of standard representation. Here it's using this scientific notation. It's 1 times 10 to the power minus 10. That's what this notation means. So if I actually just type that value as I just wrote it, well, actually, I can't see how many zeros I've got. Not quite the same. You can see that it doesn't actually literally print it. That is a value, but it prints it out slightly differently for this particular example. So what should we print out when we want to show these values? Well, we just want to show, if we have hearts, we just want to print hearts. Just like when we have true, we just want to print true. So it's no big deal. But it'd be really boring if we had to define that function ourselves, right? If it's hearts, then we print out hearts, if it's club. So fortunately, there's a nice mechanism to define that automatically. We add to our data type declaration, we indent, because it's part of the declaration, a deriving clause, and we use the word show with a capital S. So this show with a capital S, this is called a type class. It's kind of like a club. Some types are in this club. If you're in this club, so to speak, then you have a show function that you can use to print things out. So this is basically saying automatically provide a show function for this data type. And if you have such a function, then when we type clubs, it will be able to actually print them out on the screen. Okay? So it looks like a bit of magic, and it is sort of magic, but it means that we don't have to manually define the function to print out the clubs string on the screen. Any questions? Okay, a little bit tedious maybe. Let's give another example. Every playing card has a color. We can work it out from whether it's a clubs. Clubs and spades are black, hearts and diamonds are red, right? So if we want a function that given a suit gives us a color, we could represent a color as a string. But then there are lots of different strings that have nothing to do with colors. So it might be more practical and more useful to define a data type for colors. So let's do that. It's a new type. It always begins with a capital letter because all types have a capital letter in the name. It's either red or it's black. These are two values of that type. They also begin with capital letters when we're introducing new values of a type. And if I want to be able to print them on the screen, I better add this deriving show clause here. Okay, so let's define a function. We've defined some new types. We haven't used them for anything yet. So let's define a function. Let's call it color. And it's going to be a function, small c, which when we give it a suit, will give us back the color of the suit. So the type of this function would, you give me a suit, like one of these guys, and it'll give me back the right value. So let's define it first using guards. So if we have a card a suit S, if the suit is equal to hearts, or the suit is equal to diamonds, then the answer should be it's a red card. Otherwise, it's a way of saying whatever you get, if that's not the case, it should be black. Okay? Now I could have split this over two cases. If you don't like these, and that was relating to a comment we had earlier, I could say that, oh, well, let me do that. It maybe is nicer to read if I write it like that. So I'm going to copy that case here. There are two red cases. Otherwise, it's black. Okay. Is that nicer? Okay. So we're combining guards, and we're saying if S is a heart, then it's red. If S is a diamond, then it's black. Let's try and load that function. Sorry, my hands are not working very well today. I get an error. So it's similar to the error we got last time when we tried to print something on the screen. It's this no instance, blah, 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 arising from use of equals. So we've got a similar situation to we had when we tried to print out the value. In order to test whether two things are equal, we need an equal testing function. When are two things equal? And not all types have an equals testing function. For example, we can't ask whether two functions are equal in Haskell, because in general, it would take an infinite amount of time to do that. You'd have to check all the inputs and all the outputs. So not all things in Haskell can be compared with this equality operator. So how do you get to be, which types can you compare with equality? Well, it's the types that are in another one of these clubs, not the show club, but the EQ club. So if you're in the EQ club, then you have an equality operation. And again, it would be really boring to have to define the equality operation when it's the obvious one. So fortunately, we can play the same game that we did before. We can derive that automatically by saying, I want not only the show function to print things out, I also want the equality operations, equals, not equals. Okay, so this will automatically allow me to test for equality. If I recompile this, I still seem to have an error. it's not color that I'm testing for equality. They're quite right. It's the suit that I'm testing for equality. So I've got to put it in the right place. There'll be no harm in having it over here. We could ask the question whether two colors are the same, reasonable to do, but actually what we need for this function is this one up here. So let's recompile that. And now we can do it. And we can ask, what's the color of clubs? And it's indeed black. Okay. However, having said that, this is not the way that I would really like you to write this function. I'm going to comment it out. Because there's a nicer way, and it relates to a comment I made during the Kahoot. We can use something called pattern matching. So the normal way to define functions when we have a new type that we've introduced is to define them using pattern matching. And the definition by pattern matching is where we say, if the argument is hearts, then the answer is red. So we give more than one equation, but we actually literally say what the, in this case, literally say what the argument should be. And now we can go on, but actually we can now take a shortcut. We can say the color of any other card C is black. So it's kind of like the otherwise. So this says, to work out the color of a card, if it matches this pattern, then the answer is red. If the card matches this pattern, then the answer is also red. And if it doesn't match either of these two, if it matches this pattern, C, then it's black. Well, this is just a variable. So any value matches this one here. Okay? So this is a variable C, and we're saying if it's some other color C, then it's black. So these are examples of patterns. A single variable, that's a pattern. Or a value, that's also a pattern. Yes, question?
Is one more efficient than the other?
Is one more efficient than the other? I think the differences in this level are not significant. However, definitions using this style do not require you to have an equality operator. So even if you don't have an equality operator, pattern matching will still work. So that's one more significant difference. Question?
Does it matter where you place the general, the otherwise?
Yes, it does matter. So the question was, does it matter where I place this equation here? If I move this one up here, let me recompile that. Well, actually, I get a warning. So this is not an error. It's actually warning me that I've done something a bit weird. It's saying, it's saying that this pattern match is redundant. That means you don't need it. And why is that? Well, because this one will always match. So if I use this function, if I say color of clubs, one of those black guys, it's fine. But if I ask for the color of diamonds, I'll also get black. So these equations are used in order from top to bottom. Okay? So the order is important if the patterns overlap, as they are described in the warning message you get.
So you cannot use pattern matching to include special cases in an otherwise defined function?
You take the special cases first, using pattern matching, and then you do the general case afterwards. Yeah?
Could you define some special cases for a function and then use an expression to define the rest of the
Can you use special cases to define a function, then some expression? I suspect the answer is yes, but without a concrete example of what you're thinking of, I'm not sure I can give an example myself.
Thanks.
Now, there is another pattern. We've seen two patterns here, where when you have a value or when you have a variable. There are actually lots of patterns. You can combine these things. But there's one special pattern that is not something you will see on the right-hand side of the equation. And that's something called the don't care pattern. Right? When there's something and you don't care what it is, the pattern you use for that, just to make your code a bit more easy to understand, is an underscore. Okay? So this is called the don't care pattern. And what is special about the don't care pattern is you can't use this pattern over here. So basically it says, whatever it is, I'm not going to use it. It can be anything you like, and I don't care. Okay? If I write C, then it means I might want to use the card C over here to do something else with it, inspect it with a different function. So this would be maybe the typical Haskell style of writing such a definition. Any questions? We'll see this example popping up in more examples soon. Okay, let's move on to the next thing. So that was talking a bit about pattern matching. So let's move on in our job of defining a data type. And I've started, but I haven't finished, defining a data type for the rank of a card. So you know all these ones, Jack, Queen, King, and Ace. But that's not quite enough, because there are lots of other cases. There are the cases of 2 and 3. And so I could define the data type in this way. I have one, these are called constructors, to construct the values. One constructor for each card, each rank of card. But actually that would be a really tedious way of doing it. We might have functions with pattern matching with 14 different cases. So when you're doing modeling of data types, there's always a bit of a trade-off between precision, modeling exactly what you need and nothing more, and convenience. Now, in the case of playing cards, I think it's more convenient if we use an int to represent the numeric cards from 2 up to 10. That will be much more convenient. We can add them together, for example, more easily. We can compare them more easily. But the price we pay for doing that is that our data type will now also contain a lot of junk, because we might have a card whose value is 99, and there is no card that has value 99. So we make a trade-off between precision in modeling our domain and convenience. Okay? So I'm going to make the convenience choice and model all of these things, all of the numeric cards using a number. But how do we do that? Well, whenever we define a data type, we have to define new constructors. These are all new constructors, Jack, Queen, King, and Ace. But what I'm going to do now is I'm going to just give a new constructor called numeric. And the difference between this constructor and the others is that a numeric value will have some content. It will contain a number. So these things are just values on their own. This one is going to contain a number. So how do I write that down? What's the notation for doing that? Well, the contents of this will be written as a parameter of this constructor. And the parameter is going to be an int. So numeric here is a thing I'm going to use to build values. But this thing here is a type. So what I'm declaring is that a numeric is a constructor that contains an int. And I have to give some examples of this to make this clear. So what's the type of a Jack? It's a rank. What's the type of numeric? Is it a rank? Not quite. It's a function. If you give it an int, it becomes a rank. So let's try it out. What happens if I apply numeric, it's a function, to an int? 2. Well, that is a value. Numeric 2 is a value. Numeric 2 is a value. What is its type? It's a rank. Because numeric was a function that if you give it an integer, it gives you a rank. So when I apply numeric to an int, I get a rank. Okay? So we have not only, so this is no longer what we call an enumeration type. It's not just a list of different new values. This one is a little bit different. So they're different two, you could say there's kind of two kinds of values that you can build of this data type rank. The kind of boring ones, Jack, Queen, King, and Ace. And the slightly more interesting one, a numeric and then an integer. So I could build a list, for example, of ranks, Jack, King, numeric 10. That's a list of ranks. It doesn't print anything different than what I typed, and that's because this thing here, copy it, paste it, is just a list of ranks. They're just examples of ranks. Okay? So now I have a way of modeling the rank of a card, but there is a slight, as I mentioned, a downside, and that is I can have a numeric minus 19. That's a perfectly valid member of this data type. And that's not so nice. It's quite useful, I think, when we're going to test programs using cards to define the property that we expect for all values of this type. And the property we expect for all sensible cards, all valid cards or valid ranks, is that the number that we have in the numeric case is between 2 and 10. Okay? So let's define that as a data type invariant. I'll use a quick check style notation. I'll call it a prop. It's something that should always be true in our programs. If our programs start producing a numeric rank bigger than 10 or less than 2, then something's gone wrong. So let's define a property. I'm going to call it prop of rank. And it's what we call a data type invariant. It's something that should always be true. It's invariant. It should never change for this data type. So if it's going to be a function from a rank to bool, it's going to be tell me if a rank is a good rank. So let's define it by pattern matching. So we could start by taking the sort of easy cases. We could say, is a king a proper rank? Yes, it is. And we could go through them, queen, jack, ace, but eventually we're going to have to deal with the tricky one. But actually it's going to turn out easier if we do the tricky one first. So let's do the tricky one first. So we need to do a pattern matching on a numeric card. So what is the shape of a numeric card, a numeric rank? Well, it's the numeric constructor applied to a number. So the shape, its pattern is, I'm going to need brackets for this, numeric applied to some number n. Okay? So that's a pattern which will only match the numeric cards. N will be an integer, and numeric will only ever match if it's a numeric card. So what do we do when we want to apply this function to a numeric card? Well, we need to check that the value of n is in the right range. Namely, n has to be bigger than 1 and n has to be less than 11. So if this gives you true, then this card is a valid card. What about the rest of the cases? Well, the rest of the cases are all valid, right? You can't have an invalid jack or an invalid ace. They're all valid ranks. So it doesn't matter. We don't care what it is. If it's not a numeric card, then it doesn't matter what it is. Who cares? We know that it is a good card. So that's a definition of a function which just tells us whether a given rank is a good one. Any questions? All right. So the typical place where we might use this is if we have functions that are manipulating cards a lot. We might want to make sure that when we produce a card that the ranks are all valid. And this is a function we could use as part of another checking property. Okay, so if you want to look at a longer example of a function, we can define when does one rank beat another? Well, an ace beats a king beats a queen beats a jack beats any numeric card, and one numeric card beats another if the number in one card is higher than the number in the other card. Okay, so we know when one rank beats another. So you could easily define, well, easily, maybe not, you could define a function to do that. So there is a function in the notes, and I'm not going to go through it in detail because that's not the main point of the example. I'm going to show it to you, and it's developed sort of step by step in the example. Okay, so it's complicated looking, right? There are lots of cases. And there are maybe some slightly simpler ways to do it, but that requires us to get into a whole load of other stuff that we don't want to do now. The point of the example here is that maybe once you finish writing this down, you're not really sure whether it works or not. I mean, the idea is that if the second card is an ace, then the first card can't possibly beat it, right? There is no card higher than an ace, so an ace cannot be beaten in rank. So that must always give false if the second card is an ace, right? Yes?
What about another ace?
They would be the same then. You don't beat an ace with an ace, you kind of draw.
Yeah, but wouldn't it turn false if you...
Yeah, so two aces would give you false. An ace is not bigger than an ace, just like one is not bigger than one.
An ace was...
Yeah, maybe in some card games, you're right. So there's some exact semantics of what it means to beat. Depends on which card game. We've chosen the example where you have to be strictly higher to beat. That's what's been coded here. I think, okay, so you can wrap your head around the logic of this, whether this makes sense or not. But you can see at least that it gets a little bit tricky. I think maybe this is the interesting case because we've only just learned about pattern matching. So this is the case that applies when both cards are numeric. If both cards are numeric, they both match these two patterns. They're both numeric cards containing numbers m and n, and this card beats this one exactly when m is bigger than n. But the point of the example here, Rebbe, is not so much this, but how might we test it? Well, we might test it by defining a property and doing some kind of testing on that property. And we'll use random testing because that's what we're doing. Actually, you could use other kinds of testing. There aren't so many different possible cards. So let's define a property of rank beats. If we have two ranks, rank 1 and rank 2, here's a possible example. Here's a possible property that you might write. And I'm going to introduce another little trick, which is this one here. When you have a function like this that compares two things, sometimes it's easier to read it if you write the function in between the two arguments. Like you write plus between the two arguments, 1 plus 2. It's an operator. Rank 1, rank beats rank 2 is easier to read than rank beats rank 1, rank 2. The meaning is a little bit clearer. And in fact, you can actually do this as valid Haskell. If you want to treat a function which has at least two arguments as an operator, you turn it into an operator just by putting these little backward ticks around the function. So here's a possible property. Rank 1, rank beats rank 2, or rank 2 beats rank 1. So that might be a possible property that you might expect, maybe. Okay, so I've just used this function twice. Either rank 1 beats rank 2, or rank 2 beats rank 1. Now, in the light of the discussion we had a few minutes ago, maybe you see that's not quite right. But let's suppose that was our first guess at a reasonable property for rank beats, and we want to test it. So how do we do that? Well, do you remember we used quick check in the first lecture? And we applied quick check to one of these property functions. And in order to do that, we had to make sure that we've imported the quick check library in order to get the quick check function. It's not one of the standard functions in the so-called prelude, which is where all the standard functions live. So we have to load it by using that library. So we can do that. We have to reload our code. And we can try that. But it doesn't work. And we get another one of these kind of error messages that says there's no instance, blah, blah, blah. And this relates to the fact that in order for quick check to work, it needs to generate random values. And it knows how to generate random values for loads of stuff, but it doesn't know how to generate random values for the data types you just defined. We need to actually help quick check by telling it how to generate random values for a new data type. For example, we need to tell quick check not to generate numeric cards where the number is smaller than 2 or bigger than 10. There's no way for quick check to know that cards should have that property. I'm not going to tell you in this lecture how to do that. We're going to actually cover that in the near future, in a week or two's time. What I am going to do is uncomment a bit of quick check magic that will make that work. You get to see what it looks like up here, but I'm not going to explain it. So for now, you have to trust me. There's a way, and you'll learn how to do this yourself soon, of generating random, or telling quick check how to generate random values. So if we do that, then we should be able to run quick check, and we can, but the property fails. And it fails for this reason we discussed earlier. Does a king beat a king? And according to this definition, a king doesn't beat a king. The only thing that can beat a king is an ace. That's just the way. So you can either view that as an error in the definition, or it might be an error in the property that we expected to be true. Either way, something needs to be fixed. I'm going to fix the property saying, I think this is really what I wanted. So how do I fix the property? Well, there's a third case. If you take any two ranks, either rank 1 beats rank 2 beats rank 1, or they're the same rank. One of those three cases must be true. Okay. So they're the three cases. I can reload that, and I can recheck. And now it passed my tests. And if you don't really believe it's actually done any work, that was a bit quick, you can type verbose check and the same property. And if we do that, then it will actually print out all the test cases that it generated. And let's have a look at them. And actually the generator was smart enough to only generate real values and not stupid values like numeric minus whatever, but it actually wouldn't make any difference for this test. So you can see that quick check really did do a lot of work in testing all those values. Any questions? All right, let me just bring this all together with the last part. We've defined a suit and we've defined a rank. A playing card is a thing which combines those two things. And we can combine those two things together in a number of different ways. One of them is to define a new data type for cards. So that's what I'm going to do. It's not the only way. And this data type is a little bit simpler in some ways than the other ones. What is a card? Well, how many different options are there? I would say there are no options. Every card is the same. It has a rank and a suit. Yes, there are lots of different ranks and there are lots of different suits, but every card has the same shape. It contains a rank and a suit. So a card is a data type where there's only one kind of thing. So there are no vertical bars in the definition. We haven't got any choices between numeric and non-numeric. But it contains more than one thing. Just like a numeric contained one thing, an int. This would be a type that contains two things, a rank and a suit. So when a data type, there's only one kind of things in a data type, there's a common idiom, a common way of writing the type, and that is to use the name of the type to be the same as the name of the constructor. A bit confusing, but we'll get the hang of it, and this is the standard way it's done. A card, so this is the type, and this is the value constructor, also called card, contains two things, a rank and a suit. So that is our definition of a card, deriving maybe equality. Do we want to check cards for equality? In a normal game of cards, there is only one of each kind. Testing for equality might be useful to check that nobody's cheating. Of course, we want to print them out as well, so we want to be able to show them. So that's an example of a card. And that's what I want to leave off for now and pick up in the next lecture and show some examples of programming with cards before we start digging into lists. Any questions in the last minute or two before we finish? All right, I think you look like you've had enough. So that's all for today. Thank you.